Welcome everybody. Welcome back to another lecture on quantum field theory, a first course on quantum field theory and quantum entanglement. So, in the previous lecture we have stopped at, so we were looking at how to compute cross sections essentially. So, we were looking at all these contractions and everything. Now, you can go coming to the introduction of Feynman diagrams and how to compute this in a 5-4 theory. So, the theory we were looking at is a 5-4 theory. Along the way we introduced some Mandelstam variables, which are the kinematic variables in a given process. So, let me continue doing this business essentially. So, what we have is so what we have, all these Biggs theorems tells you that tells us that in general we have a time ordered product of some phi x1 phi x2 so on phi xn. This is equivalent to normal order product of the same thing, phi of x1, phi of x2, phi of xn plus all possible, these two dots I hope you can see them, okay. This is normal ordering, phi of xn, phi of x2 contraction, and the remaining ones just remain the same, and so on, so on. So, then you will have all possible contractions essentially. The last term will be all possible contractions essentially. So, this then we can proceed further to calculate these things. Now, the two body contraction we realized it is just nothing but your propagator essentially. It is a straight line essentially between these two. Now, you can, I will introduce a complete detailed connection between calculating S matrix elements essentially. But before that, let me just tell you something interesting essentially, that you can use a graphical method to calculate the S matrix elements. And this graphical method and is called using Feynman diagrams. Okay. Now, I will come back to these contractions and everything. So, you get this picture. So, now, so what we have, each contraction, okay, 2 point there could be 2 point contraction, 3 point contractions and so on. So, essentially, and one of them will be the 2 point contraction, we know, we have seen it as just the propagator, because it is just a time order product of two of them. Now, suppose if you have a 2 point contraction, you can represent it in a, so you want to represent everything in such a way that you can be able to calculate it everything in terms of graphically, okay. So, a 2 point contraction I will represent by a dot in this manner essentially, okay. So, this is between x and y, say, or x1 and x2, so and so, for example, okay. This is a propagator, 2 point contraction essentially, and then you can have all possible other contractions like, so its 4 point contractions would be like this. You can have and so on, so. Okay. So, if you have 4 point contractions, similarly you can have sorry, this as a, so in your Lagrangian you only have 5 4 theory. Now we will remember what our Lagrangian is. Essentially you have del mu phi dagger minus m square dagger phi plus lambda phi dagger phi whole square. So you have 2 point correlations, and then you have 4 point contractions, and so on. So you will have all these things which emanate in your theory from your Lagrangian. Essentially whatever your Lagrangian, only the relevant ones which will be useful are the ones which are present in your Lagrangian essentially. So all these contractions can be represented graphically in this particular fashion, and it will turn out that only the connected diagrams will play a role. Essentially only the connected diagrams in computing the S matrix elements. Essentially when you are remember our Lagrangian is this essentially. So you have all this bunch of these things. So what we want to see is, given the Lagrangian, what are all so let us see what are the possible contractions you will have from the Lagrangian. So from the Lagrangian you now before going into the proceeding everything through the Wick's theorem and everything essentially, and going through something called the LSG reduction formula, before going to that I just want to give you a flavor, like I promised to you, that how to use Feynman diagrams. So given this Lagrangian, the Feynman diagrams tells you that there is first of all a propagator for the scalar fields, which is nothing but a 2 point contraction. So the things which will be important in calculating S matrix elements for this given Lagrangian are a propagator for this field, the scalar field essentially phi, Klein-Gordon field for the phi, which carries a weight p square minus m square plus I epsilon with the prescription of the Feynman prescription. The I epsilon is the Feynman prescription for the propagator. This will again remind us which pole to take when and everything essentially, which I have spent some time essentially. Then other thing, okay, is there is a 4 point interaction vertex with a strength I lambda. This is called vertex essentially, and this, so let us take all of them to be incoming for some reason essentially. So I will tell you this is coming from this term essentially, this term, this term gives you this vertex essentially, this particular vertex essentially. This tells you that there are 4 fields sitting at the same space time point, okay, and this is called a vertex essentially, and this carries a strength I minus I lambda. So with this, these 2 things which are required to calculate the S matrix elements or the amplitudes essentially using graphical techniques are called Feynman rules. So you need, in principle, this is a completely different method essentially. It has its essence in the contractions, in the Wick theorem, in the a Dyson series and so on. So, but at some point what you do is you forget about all that stuff, you forget about the Wick theorem, Dyson, and I will justify the reason in coming moments essentially, but you forget about all that and you say that only connected you say that I write down some graphical rules given the Lagrangian, which is called the propagators. What are all the propagators for every field in this theory, and what are the interaction vertices for this particular theory. So, given these propagators vertices, I can now start calculating my amplitudes or the S matrix elements for a given given process. Say for example, let us take phi scattering to phi. So, this is equivalent to say pi going into pi, or a pion going to a pion scattering and so on. So, now this can be, now I want to visualize this particular scattering diagrammatically. I want to visualize this particular scattering diagrammatically. I will write down, draw all possible diagrams using these vertices, okay, using these vertices, and I will also write down two other Feynman rules, which is an incoming phi, and this is an outgoing phi. Okay. So, there are two more Feynman rules, propagators, vertices, and the external lines. So, similarly I have incoming phi star and outgoing phi star. This way I will represent it with an opposite sign. So, the incoming phi and phi star each will come, there is only because it is a scalar particle, it does not have any wave function except the plane wave. So, the solutions of the Klein-Gordon equation are nothing but the plane wave, there is no polarization or anything because they are spinless, and they are okay, and so each of them will carry an exponential the plane wave factor. So, each of them will carry the appropriate plane wave factor. Okay. So, even if you do not keep it, this plane wave factor will end up giving you something at the end of the day. So, what I want to draw is this particular thing, like phi going into phi essentially. So, the incoming phi I will draw it in this particular fashion. There are two phis, and then there are two outgoing phis, essentially the outgoing phis. So, this is the leading order vertex. So, the leading order vertex, and then for each incoming I have to define, because each of them has its own plane wave factor. So, each of them will have its own momentum P1, P2, P3, P4, and this is exactly the vertex we have seen here. Essentially this is the vertex. So, this amplitude I need to calculate. So, to calculate this amplitude I only have, there are no internal lines because all of them are external lines essentially. So, because if phi comes, interacts and then goes away essentially. So, at the leading order in perturbation theory, what you have is you only pick up minus I lambda, then you also have to, each of them will carry a plane wave factor. So, this amplitude we want to represent by some factor I m. So, this will be I lambda delta power 4, this is purely coming from the plane wave factors. So P1 plus P2, these are the momentums, P3 minus P4. There is also 2 pi for 4 essentially, I P4. So this amplitude is nothing but the momentum conservation. This is nothing but 4 momentum conservation which is imposed at every vertex. Okay. So the simplest process you have seen, okay, you have calculated the amplitude already. So the amplitude is nothing but lambda essentially, because it is just only one interaction. Okay. Okay. In this case, you have this particular this momentum conservation, because you have to, the momentum is conserved at every vertex, because you have energy momentum conservation or 4 momentum conservation, it should happen at every vertex. So given this, so now what about, now this is your calculation of amplitude, and then this is your S matrix element. So what I am saying is that your S matrix, which is 5 phi, and the outstates are also 5 phi, incoming and outgoing, goes as this equation 1. Okay. So you have calculated your first amplitude without actually worrying about various things, just by using Feynman rules essentially. Okay. So these Feynman rules will not tell you the Dyson series, they won't, they are directly written, you write it down carefully from the Lagrangian essentially, but they can be justified. They can be justified from all the techniques which we have learned, meaning that the ones like the Dyson series, the mode counting, the Dyson series, and then computation of the propagators, and the Wick's theorem, and so on, the contractions and so on, so essentially. Okay. So, and you can calculate this order by order essentially. That means that you have calculated at the leading order, say for example in leading order in lambda. Now what happens if you have the same scattering crosses? So 2 incoming phi, 2 outgoing phi, but in between a couple of phi, okay, are absorbed, okay, are radiated and absorbed essentially. So these are called virtual particles. They are off shell, they are not on shell, and I think we discussed in the relativistic quantum mechanics course, I am sorry to refer it again and again, in great detail about this virtual particles. Essentially they are not on shell. So for a tiny period of time they do not obey in principle this energy momentum conservation sort of thing, that meaning for a tiny period of the time they don't follow their own dispersion relations, they are away from their mass shell. Okay. So these are virtual particles which are created and destroyed with periods of time delta E, delta T, H cross essentially, the tiny periods essentially. So these virtual C can affect the amplitudes essentially at higher orders. So you have, now how do you calculate this higher order in this thing? Here you have one vertex, you have two vertex, number 2 vertex here. So there is an I lambda factor, there is an I lambda factor here, and here you have propagators. Now here this amplitude, let me call it m2 because it is second order. How would I calculate? M2 is equal to the first vertex I lambda, then there is a propagator, this propagator, but before calculating I need to assign some momenta essentially. Okay. So, P1, P2. Now this momenta, okay, the internal momenta, these are different momenta essentially. So this momenta, so this will be, if I give you something like Pk, for example, this will be K. So if I give this momenta K, this one would be P1 plus P2 minus K, because at each vertex, as I insisted essentially, that the energy and momentum should be conserved. Okay. So I hope you see the notation. Okay, let me just change the color for the lines at least so that things will be clear. So this is your Feynman diagram. Okay, this is your assignment of momenta. Okay. So at each one you start with the incoming vertex, essentially one vertex and the second vertex. Okay. You start with I lambda, the vertex gives you the incoming particles, they do not have wave functions, they only have the plane wave factor. So you have P1 plus P2 coming in essentially, and then there is a propagator because it is a virtual propagator. Then the propagator goes as minus I k square minus m phi square essentially. And what about the second propagator? The second propagator is I P1 plus P2 minus k square minus m phi square, and then you close with the propagator. So now you see there are two distinct classes of momenta. Okay. One is the momenta which is internal. Okay. So this k which is internal momenta, okay, which is so k is the internal momenta for particles which are virtual. So these virtual particles are not the eigenstates of the free Lagrangian. So they are not in states or out states essentially. Yeah, they are okay. Yeah, they are eigenstates of the free Lagrangian, but they do not lie on the momentum shell. Yeah, and these ones are external particles. External particles which are in and out states essentially. They carry a definite momenta, they carry everything essentially. So they are sort of eigenstates of the free Lagrangian. So in fact it will turn out that the propagator is nothing but the sum over all possible states of the free Lagrangian essentially. I think yes, one can see it in this thing. So they do not so this internal momenta is not it can have, it is free, it is not conserved by any energy momentum conservation laws. So in principle when you calculate this amplitude and when you do the calculation of the cross section essentially, you have to integrate, one has to integrate the internal momenta from minus infinity to plus infinity. Okay. So one has to integrate the internal momenta from minus infinity to plus infinity. So this is So this is a big thing essentially. So we will see this will lead to some complications, essentially some complications called divergences and so on. So anyway, so the basic point of this entire exercise is that using these Feynman rules starting from the Lagrangian, essentially you can calculate all the S matrix elements without where the underlying thing is essentially given by the Dyson series Wick's Wick's theorem and so on. So, but to close this we have to justify why how we are using this Feynman things, essentially how we are using the Feynman rule graphical method. So for that I will, so with this I can calculate the cross sections essentially. So I can calculate the full differential cross section. So given by this amplitude I have got. So this the differential cross section, you can check it out, will be given by 4 E1 E2 V, some volume factor, and then there is a flux. So and then mod m square essentially. So essentially okay, and then you also have the phase space factor. So if for a simple 2 to 2 differential cross section is given by this particular fraction, so you put it back into this amplitude. So the amplitude goes as a square of the cross section goes as a square of the amplitude. Now I will leave it to exercise to calculate this the details of this using something called the Fermi golden rules essentially. Okay. So this will be part of the exercises, okay. So which you will use it essentially. Now, but before going further, I wanted to introduce something essentially which I will go through. Let me formalize the use of Feynman diagrams essentially. Okay. Now, how do you justify, because of all the Wick's theorem and so on, so your the Dyson series and everything. Okay, how does one justify? So, how does one justify the use of Feynman rules from Dyson series Wick's theorem, etc. So this justification is a little bit formal and it ends up giving you something called the reduction formula. I will not prove many things, but I will just go through the justification a little bit essentially. So the overview of the justification is as follows essentially. So okay, so the overview of the justification as follows essentially. Now in an interaction theory, the vacuum is given by it is not the point is that it is not equivalent to 0. Okay, the interaction theory vacuum is different this. Okay. So, but what we do is we say that the Hamiltonian acting on the vacuum should goes to 0, because we have to normalize. Okay. So, we have to normalize the thing essentially. So, what we will do in principle, any Green's function in an interaction theory would be defined as g of n. We have defined Green's functions anyway of n dimension. So, x1 to xn is equal to time order product of phi h x1 h is the Heisenberg h, but all evaluated in omega essentially, all evaluated. Okay. Now it turns out okay, by some theorem essentially we can show that this object on the right essentially, which is the time order product, which we have been calculating all this time essentially, turns out these Green's functions, or what we have shown so far, is equal to acting on vacuum time this 0. Okay, note this thing, instead of omega I am using this essentially phi of x1 phi of xn with phi I, not phi h. Okay, instead of the phi I fields, which are essentially this, times s divided by S 0. So, S is nothing but your S matrix essentially. Okay. Now, the proof is long, and can be found in Peskin Schroeder's book, and of course Peskin and Schroeder's book will be there essentially. Okay, you can find it there. So, now you see the important point is that when you are calculating any Green's functions, it is equivalent, or S matrix elements, it is equivalent to calculating over the free vacuum essentially, over the free vacuum time order products of these Green's functions and divided by the S matrix, which is only acting on the vacuum. Now, if X matrix acting on the vacuum, what does it mean essentially? So, the S matrix acting on the vacuum is in phi 4 theory, let us say for example, what is and what is, so here again we can use the diagrammatic approach because we are not showing the proof in great detail essentially. So, this is, it can be shown, is nothing but bubbles. So, you have vacuum bubbles at all orders. There are no in and out states. So, these are bubbles which are going from one to meaning the vacuum turning it itself, but in interaction manner essentially. So, plus so all these vacuum bubbles, these are all okay, these are all possible essentially, and okay, this set of diagrams ends up being a series essentially. This entire thing is an exponential series. So, this is exponential of that is it. So, this is the vacuum, okay, amplitude of vacuum of the free theory to evolve into itself is exponential of all possible distinct possible. Okay. all possible distinct bubbles. So this means that one can show that what you will end up having is that the numerator here, okay, is nothing but all the connected diagrams, essentially all the connected diagrams. So this means that the time order product of phi x1 phi xn s, this is nothing but sum of all connected diagrams times this exponential of vacuum bubbles. So when I say connected diagrams means at least one leg is connected to external diagram, connected to either in state or out state, okay, is connected to the in state or something, essentially, okay, one of these states essentially. So you end up having disconnected diagrams. We have seen examples of disconnected diagrams, right, in a lot of this, okay. So we only need to worry when you are calculating S matrix elements, we only need to worry about connected diagrams, and that is the reason why only those diagrams will play a role in the cross sections or amplitudes or the Green's function calculations essentially, and all these things will just cancel off. These bubbles, okay, will just becomes 0, because in the final thing of the Green's function, this bubble which appears on the numerator as well as the denominator just cancels off essentially, okay, just cancel. The numerator on the other hand, okay, is given by this particular thing essentially, okay. So these Feynman diagrams are essentially this. Finally, what we can show is that, okay, so these Feynman diagrams are nothing but your S matrix elements. That is the reason why this justification works. We can make it much more concrete essentially in terms of these Green's functions essentially, okay. Now we can, let me write the S matrix elements essentially with in and out states P1 n prime P1 Pn, this is equivalent to minus psi, okay, let me call this n prime, this is n plus n prime pi I is equal to 1 to n prime pi prime square minus m square pi j is, this is nothing but the phase space factor essentially, okay, on shell factors, okay, pj square minus m square, assuming all the particles are, times g, okay, let me write it down neatly, times this g times g is the Green's function n plus n prime minus p prime minus Pn prime P1 Pn. Okay. Now this is nothing but the Fourier Green's function. That means G, this is the same G, okay, G P1 Pn is equal to integral pi dx4 e power I pi xi I is equal to 1 to n. This is nothing but the Fourier transform g of n x1 to xn. So you take the Fourier transform of the Green's functions, that is what we do essentially, and when you calculate it, putting everything in terms of this mass shell, you end up having the S matrix elements essentially. Okay. So you do not care about of all the external particles on shell, all the external particles should be on shell. So this is the LSG reduction formula. This has a technical name which goes by the name LSG reduction formula. So this justifies why the Feynman method completely works, whereas this thing, this entire thing, okay, what we have derived, this is a crucial point, right, the derivation essentially, which has a long proof we have started with, which we have skipped essentially. Okay. So this long proof you can find it in Peskin and Schroeder and various things. So the Green's function is given in this particular function. So starting with this, you can show the S matrix elements. You can forget about all possible other diagrams, and only those diagrams are relevant which are connected to the external lines essentially, and those are the only ones which contribute to your S matrix elements, and this can be shown beautifully by LSG, the Dyson series, Wick's theorem, and so on. So, and that is the main reason why the Feynman method works so much, so very well essentially. Okay. So I will stop here. I had a longer class today, but I will stop here. So I will revise in the next lecture a little bit more essentially, just to hone down this point, and then we will move to some other the fermionic fields essentially, and then we will move to fermionic fields. Okay. Thank you very much. I will stop here. Thank you.